be done in a transparent and responsible manner. So we're going to conduct a lot of research in this program across a number of different axes. So we're going to be funding some modelling work, prediction. We're going to be funding some monitoring of the climate and of natural analogues. We'll be funding work to take data and try and make it statistically significant. And we'll be funding societal aspects around the development or the research of solar radiation modifications technologies. So can they be ever governed? How will they be governed? Ethical implications, public perception, things like that. Also in this program, and quite crucially for our goal of obtaining this robust data to underlie effective governance, in certain circumstances we'll be allowing small, controlled, outdoor tests in the real world of some of these approaches to really find out how they work and what they might do. And all that will take place under rigorous governance, which I'll talk to you about in a minute. Governance, in this case, of the research. I certainly don't hold with the idea that research is a slippery slope to deployment. I think that the information you gather from research can be used in certain circumstances to actually prevent deployment by showing you what is damaging and what is harmful. And what research does do is it builds an evidence base for us to make informed decisions on whether to develop approaches further or whether to discount them from their use. Conversely, if you don't have that evidence base because you didn't do the research, we cannot expect any policymaker to listen to anything that we say, and they will just come up with decisions based on their own gut feeling. And so we have to supply that evidence if we want sensible decisions to be reached. So how are we thinking about running this program ourselves responsibly? So firstly, we committed to these high-level principles that I've shown here. We established an independent oversight committee to hold the program team and ARA itself to account. And we committed that we would fund research, particularly for outdoor experiments, and in fact for all the research that only answers critical pressing questions that has to be justified. We're not just spending money here on things that interest us, but really where there is a key need to understand particular parts of what's going on. We are working towards having our teams design their experiments so that they're safe by design to minimise risk as far as possible. And for teams that are doing work outdoors or for monitoring studies, we're going to insist that they engage with key communities and co-design their experiments with them in a respectful manner. As a program level, and also for the projects, we make a commitment that we're going to communicate proactively and transparently, so get that information out in a way that can be understood by a variety of audiences, acknowledging that we feel is contentious and maybe broader implications, and that we may need to adapt our strategy as we learn more about the field and as it develops around the program. We can't remain static. So in practice, we have a few mechanisms that I'll just run through very quickly. I won't go into huge detail, just to show you some of the ways we're thinking about having governance in practice. So in the thesis and solicitation documents we published, decision trees, here's one of them, which shows you sort of governance at the technical level, so the size and scale of experiments we might permit, saying such as things as we won't permit toxic materials to be released to the environment, things like that. Rules and guardrails around which the teams have applied to the program can see what we plan to fund and what we would not consider funding. This is just an excerpt of that particular tree. We also have an excerpt from another tree here that shows how we think about how teams should go about engaging with local communities near where the experiments take place. So things like identifying stakeholders, engaging with the local community, obtaining environmental impact assessments before the experiment starts, and sharing them with the community for feedback and for revision of experimental plans, and providing all these different feedback loops for people to have their say on how the experiment happens. And we also have our independent program oversight committee, showing you the 7 current members here on this slide, which is a panel of experts in solar radiation modification, climate, and the development of new technologies from around the world with a variety of different specialisms. And they exist to hold us to account, so they scrutinise what we do, and they can make public statements either in support or against decisions that area mates. So we announced to the folks that we were going to fund on the 7th of May this year. We're funding 22 projects based in 12 countries, and a number of projects actually led or have co-investigators here at the University of Cambridge. We're funding 7 projects that have a major or taking major component or taking place entirely in the Global South. We're not doing any outdoor observative experiments in the Global South. What those projects do is they build research capacity, and they begin to allow folks in the Global South to have a meaningful voice in the conversation, which would very much affect them. We're funding 4 what we call passive monitoring projects, where we're looking at natural analogues or other things that are occurring in the climate, just to improve our knowledge of those systems using a variety of different tools. And we're also funding 5 small-scale outdoor experiments, which I'll just tell you a little bit about now. So we're funding an experiment led from Cambridge Centre for Climate Repair involving real ice and Arctic reflections to not-for-profit space in the UK and in the Netherlands, respectively, to look at sea ice rethickening and examining the feasibility of that and its implications for local ecology and how long that ice might be. And just basically try to understand if rethickening Arctic sea ice could ever be a feasible way of trying to prevent Arctic sea ice melts. We're funding 3 projects that are looking at different aspects of cloud brightening. So we're funding a team based on the Great Barrier Reef in Australia who have been doing cloud brightening over the Barrier Reef to attempt what's called shading for a number of years. So we'll be continuing to fund that work. And a team allied to them based out of the University of Manchester that will be trying to do cloud brightening in the United Kingdom off the coast. And then a team at the University of Reading who will attempt to do cloud brightening not using sea salt spray, as the other 2 groups are doing, but using electric discharge, using initially fogs to see if we can disperse or brighten the fog, and then moving on to clouds later on, if appropriate. And finally, the final outdoor experiment we're funding involves looking at materials that have been proposed for stratospheric aerosol injection and how they age in the stratosphere, and we'll be using, or QCD will be using this nifty balloon that sends up this gondola into the stratosphere. A tray then slides out from the balloon when it gets to the stratosphere, exposing microscopic particles of these tantalum materials to stratospheric conditions. And then, after the experiment is concluded, the tray retracts back into the gondola, the balloon descends, and those samples are analysed by scientists on the ground. So no materials are released into the stratosphere when we do this, but what it does allow us to do is to see what effect the stratosphere has had on the surface of those particles, which is really important for understanding what those particles might do if they were actually dispersed in the stratosphere. For example, do we form coatings on those particles that might break down ozone? It might tell us that using these scales would be a bad idea. So the programme, I really hope, can make a positive difference in a contentious field. As the world warms, the debate around using solar radiation modification is only going to get louder. And in that regard, there is a real pressing need for rigorous and unbiased scientific research that's free of any particular agenda that can feed into more effective governance of what we're doing. The work the programme supports will be critical for that governance effort, but also the way that we do that work is going to be critical. We have to be transparent, open, and honest in the way that we do this research to bring the community along with us. And finally, just to reiterate, that we will be criticised for doing research in this field at all, as many of you have been. But we have to see that if we don't have data from the research, the options are not good. The options look like ill-considered or ill-informed deployment, or the ruling out of technologies that could really help save people's lives. And so this is why we need research now to build the evidence base to make those correct decisions. Thank you very much.
Great. So we're now going to have Jay Liss from Archipelago. What I should say is that the introduction to Archipelago came actually via my very dear colleague, Professor Hugh Hunt, and the senior person in Archipelago called Guy Newcomb. And it was getting together with Guy that actually we realised that there are lessons learned from different industries that could be applied potentially to things like marine cloud brightening. And this brainstorming of actually sort of technologies that are being developed actually in this local area by the companies such as Archipelago, we realised was really, really fruitful. And it's true for all of science and all of engineering. There are lessons to be learned by looking over the parapet from a different industry or a different context to be able to say, well, actually, what have they done well? What have they learned that we could then potentially apply rather than starting from scratch? So as a result of that, Archipelago joined with the Centre for Climate Repair in one of the proposals to the Exploring Climate Cooling Solutions, which is now called, the project's called Reflect. That's the second one that Mark mentioned, led by the University of Manchester and Professor Hugh Coe. So we're being guided by Hugh and his team, and therefore we are collaborators as part of that. But Jay, over to you.
Yeah, thank you very much, Sean. Thank you for the intro. It's delighted to be here at the Centre for Climate Repair. To be invited to give this talk, and I'm going to give a bit of more detail about the project as well, but also first I'll talk about Archipelago and our technology that we developed for a completely different field, but exactly as Sean said, we see that could have potential for this area. So my background's in chemistry, so when I first started out, we were worried about the ozone layer and getting lead out of petrol, but things have moved a long way since then. And also, me too, I don't work as a chemist anymore, I work in information and intellectual property and matters, and as I've heard about commercial contracts and IP, and I'm delighted to be part of the Reflect team for Archipelago. So I'll tell you more, Sean's given a little intro, so we'll put some more on that. Archipelago was founded by Guy Newcomb in 2012. Guy came out of the inkjet printing industry. A number of us also worked in the inkjet printing industry, which is really big in Cambridge, or historically has been. You may be familiar with life sciences phenomena in Cambridge, but there's also the inkjet printing phenomena. So we, shortly after Archipelago was founded, the team decided to do the next big thing in inkjet. And Guy others went out and talked to many people in different fields to find out what they might want to do that they can't do now. Whereas the digital inkjet printing was going to be very expensive, very small nozzles, very full colour, there are actually a lot of people had a different need. They didn't necessarily need that. They needed to be able to put down continuous coating to form a functional barrier, or they needed to put down glue, to put glue in very specific places. So the team got together and developed power drop technology, which I'll tell you a bit more about in a minute. But first of all, I want to talk about our main area of application, which is also in the sustainability field. So we now have developed the power drop technology, which you can see in a couple of pictures here. It's based around a cylinder. And you hear these things you can see it coating, these kind of multi-fibre trays. So it's a big move, particularly in Europe, to move from plastic packaging towards sustainable packaging. And that's something that can be recycled, and that gives paper a big chance to fill that gap. But paper by itself isn't waterproof or oxygen-proof. It needs functional coatings. So that's where the power drop technology comes in. It's non-contact technology, and it's industrially scalable, and it can coat all the different shapes in containers like trays and yogurt pots. So that's our main focus as application area today. And how does the power drop technology work, and why do we think that might be applicable to marine cloud brightening? So the power drop technology is based around a cylinder. We have this very small scale here, which is see-through. So you can see the nozzles go all the way through the cylinder, we call it a drum. and it has a really short fluid feed, so the material, the coating material is fed in the kind of yellow bit you can see, we call that the profile filler, and that meters in the coating into the power drop drum, and it's jetted out at the bottom onto the substrate that we want to coat or cover, and we can form pinhole-free coatings, which is a big deal. To form the barriers that you need for packaging, you need to have, the first thing you need to have is no holes in the coating, and then you may have a chance of getting an upstream barrier, water vapor barrier, grease-proof, oil-proof. So that's our main focus today. And the power drop works by compressed air. It's a pneumatic system, and it's got over 100,000 nozzles. So very, very, although it's, so 100,000 nozzles, lots of small droplets. This is a video. As Hugh definitely said, you all want to see a video of it working. So this is a video of the power drop jetting out. Sorry, that was very short. Anyway, you saw the drops coming out, so that's the power drop technology. And it's industrially scalable, it's fast. So as Sean mentioned, at some point in Cambridge, Guy, Sean, Hugh got together discussing the potential for this project. And as we, Archipelago, decided to join in as one of the partners, because we see this technology we have in power drop could be redeployed to make a lot smaller droplets, a lot more droplets, a lot more quickly with the rotating cylinder approach. So with that project then, we are part of the consortium of the team of the project, so led by the University of Manchester, Professor Bucco. Then the University of Cambridge team are looking at spray technologies, as is Archipelago. So all the spray technologies work done here in Cambridge. We're also working with experts from the climate side with the Finnish Meteorological Institute and the University of Exeter and the National Atmospheric Centre from the University of Leeds. So our first job is developing spray technologies. Will they work? Can they be developed to make the drops small enough and in enough quantity to be able to be put up into the sky to make the clouds brighter? That's our first job. And very much all of the first experiments are all going to be done indoors at very small scale compared to what would be required. We're also using modelling. There's a lot of modelling expertise in the group so that they can inform the experimental work, and it will be iterative. More about the spray technologies. So power drop, we call it power cloud for this activity. We have turned the system a little bit on its head, if you like. So the system is exactly the same with the power drop drum will be rotating. In this case, at the moment, we're just using water, but we will be using salt water at some point in the experimental, as the experiments progress, into the power drop nozzles, and then they'll be jetting instead of at the 6 o'clock position as they are now, at the 10 o'clock position, so they'll be able to go up into the air. So we're at the early stage of indoor experiments right now, but all of us are working towards experimentation into the cloud chamber in Manchester, maybe at some point next year in the spring of 2026. The other spray technologies that have been developed will all be developed here at the University of Cambridge, within Sean's team, with looking at superheated atomization, electrospray, rallojets, and bubble bursting atomization. So if you want to know any more about those, I suggest you ask the experts here after in the Q&A. The Reflect project itself, marine cloud brightening. So what marine cloud brightening, the aim is to get many millions, billions of very tiny droplets into a cloud so that the cloud will stay stable and reflect, increases albedo and reflect up the sunlight and therefore cool the land or ocean underneath. And as both Sean and Mark mentioned, in Australia, some work's been going on for some time, several years, 5 or 6 years, I think, in cooling the ocean there to save the barrier reef. The barrier reef is already hugely threatened, in some cases really depleted, and that's very sad and very important both for marine life and for Australia to keep that. So even if for humans we can wait longer for the climate to be brought back under, lowered, not necessarily the case for the marine life. The barrier reef needs that now, and so do other fragile ecosystems. So we're very pleased to be taking part in this really ambitious project to reflect, to do our bit, do what we can to help gather data, do some experiments to see if these spray techniques will be able to have the effect that we want them to. Thank you.
So we now have some time for questions. So if you do have a question, raise your hand, and then we will, I'm sure that Mark and you will do your best to answer them.
I'm just absolutely.
Okay, so Jane and Mark will do their best, and you never know, there are some other experts in the room that we could also call upon if they're from left field. So who would like to start? So please go ahead. You'll need to bellow, certainly for the camera.
Okay, thank you. So my question is about the scaling of technology. So the research will identify what might work, but there's clearly, it has to be scaled up to almost unimaginable scale, which takes time and cost. And then there's kind of energy costs and other costs involved in any of these techniques. So is there work going on in parallel to kind of construct business cases around the technologies on the basis that if the technology is found to work, we kind of know whether it's also viable?
Who would like to take this?
Well, I'll just briefly on the energy consumption side, that's certainly something that we're looking at really closely. Would it be industrially viable? Would it be really feasible with low enough energy requirements? That's one aspect.
Mark?
So on developing business cases, no, we haven't done that. And we're certainly not going to do that in the immediate future. The reason being that we're worried about basically the profit incentive in this space and what that does for the transparency of the research. So our focus at the moment is basically on doing that foundational research very much in the public good and in the public interest. If any of these approaches look like they might be feasible,